Have you ever wondered what factors affect how fast the chemical reaction goes? Chemical kinetics studies chemical reactions with respect to various factors like reaction rates, rearrangement of atoms, or the formation of intermediates. An application of this is when you take your medicine. A series of reactions in our body takes place in order to break down the medicine. If these go too fast, it will cause the patient to develop a fever, whereas if it goes too slow, the medicine may not be as effective. It's important to study these reactions in order to optimize the effect of the medicine. In this video, we'll focus on the rate of reaction by exploring the iodine clock experiment, a reaction between potassium iodide and hydrogen peroxide which yields a blue solution. For this experiment, we need solution A consisting of sodium thiosulfate pentahydrate, water, potassium iodide, and 1% starch solution, and solution B with sulfuric acid, water, and 3% hydrogen peroxide. These two solutions are mixed together, and after some time, the solution is expected to turn blue. Unfortunately for us, we threw the solution into the sink before this happened. A number of reactions allowed this experiment to work. Hydrogen peroxide oxidizes the iodide ions in an acidic condition to form triiodide, which are immediately reduced by the thiosulfate ions. Since the thiosulfate concentration is limited, some triiodide ions will persist in the solution and react with the starch to form a dark blue complex.
Now it's time to solve for the rate constant in this reaction. This is a first order reaction because the reaction rate is dependent on the concentration of thiosulfate. The reaction rate can be expressed as R equals the negative change in concentration of thiosulfate A over the change in time or the rate constant K times the concentration of thiosulfate A to the first power. These two can be equated so it can be written as the negative rate of change concentration of A over the change in time is equal to K times the concentration of A. The instantaneous rate of change of concentration can then be written as a differential equation, negative dA over dt equals Ka. Multiplying both sides by negative dt, dividing both sides by the concentration of A, we have dA over the concentration of A equals negative k dt. Integrating both sides gives us an integral of dA over the concentration of A, integrated from the initial concentration of A to the final concentration of A, equals negative k times the integral of dt, integrated from time equals 0 to the time of reaction. This gives us ln of the final concentration of A minus ln of the initial concentration of A equals negative kT. It can also be written as ln of the quantity final concentration of A over the initial concentration of A equals negative kT. Dividing both sides by negative t allows us to isolate the rate constant K. Plugging in the initial concentration of A, 0.161 molar, final concentration of A, 0.0005 molar, and the time of reaction 90 seconds gives us a rate constant K of 0.0897 seconds to the negative first power.